Aujourd'hui, on accueille donc Verena qui travaille à l'hôpital de charité de Berlin. Elle travaille notamment sur le Whipple et beaucoup sur le vaccin immunologique. Donc elle va nous faire part de leur expérience en Allemagne sur le traitement des piliers et le Whipple. Merci.
Thank you. So I'm happy to be here, as I say, and I hope that I will give you some new aspect on pathogenesis of Whipple's disease. So to start with, I'm not sure if everybody is familiar with Whipple's disease since here's the center and most expertise in Whipple's disease. I give a short introduction. So Whipple's disease was first described in 1997 by George Whipple. It's the chronic infection with Whipple and there are extraintestinal symptoms which precede normally the intestinal symptoms. There's a lot of articular pain and arthritis in the patients, and after some years diarrhea and weight loss develop, and then classical Whipple's disease normally is diagnosed from duodenal biopsies. When one has a look in the duodenum by endoscopy, this is a typical picture of Whipple's patients, but to be honest, this is not so often because most of the patients morphologically look completely normal, and this angiectasia, which are visible by these white dots, are not obvious in every patient. But when you look for the histology of the duodenal biopsy, we have this huge amount of positive material in the lamina propria, which represents macrophages that are filled with bacteria. And this is also the hallmark of Whipple's disease, these macrophages which are filled intensively with Whipple's disease bacteria. So, and just in my talk, I will first do some statistics and characterize our cohort of Whipple's disease patients that we care about in Berlin. Then I will go, the most part of the talk will be about the pathogenesis of Whipple's disease because that's my special topic. And then I will talk a little bit about immunoconstitution inflammatory syndrome, which is a major complication during the treatment of the disease. So first, for our cohort of patients. So at the moment, we care about 220 patients with chronic infection with Whipple. The age of diagnosis is around 60 years, 57 to be exactly. The majority of the patients is male, like described in the literature, but we have also some female patients. Most of the patients present with classical symptoms, that means they have chronic diarrhea. Most of them have also inflammatory arthritis, but we have also some cases which have an isolated arthritis, and there in most of the cases the diagnosis can also be from the intestine of these patients, but there are a few patients where the diagnosis could be made only from the joints or the lymph nodes. And then we have these cases where the chronic infection is isolated from the heart valves, and these cases are isolated from the endocarditis and the endocarditis. The neurological involvement, which is a much severest manifestation of Whipple's disease, is we have 24 patients from the group, around 10%, which have severe neurological symptoms. 7 of them have only neurological symptoms, which means that we have no proof of the presence of the pathogen in the intestine, but the cerebrospinal fluid is in almost half of the patients tested positive for Whipple. So we have to care about the neurological involvement in every patient. The treatment that in Germany at the moment is in most of the cases used is an initiation treatment which lasts for 14 days with intravenous saturation, and this is followed in standard for 12 months with premetazosin and hexazole orally. In some cases, from studies where it is only 3 months of premetazosin, but still the standard is 12 months of treatment. But we, at the moment, use bench experience with doxycycline in combination with hydroxychloroquine, but still some of the patients are treated only with doxycycline if the physician is not so informed about the possibility. We use minocycline for some treatment-resistant patients or patients with a relapse of the central nervous system, and in some of the patients, an interferon-gamma supportive treatment was necessary to reduce the relapse rate. We have some complications during the therapy. The most frequent complication is immune reconstitution inflammatory syndrome, which affects around 10% of the patients. Most of them are previously treated with immunosuppressive drugs before the diagnosis of Whipple's disease, and since it is really a dangerous complication because we have 4 iris-related deaths at the beginning when we did not know what iris is. Some of the patients really died from symptoms of iris. Then another major problem is the persistent problems in neurological cases. Despite the successful eradication of the tropholumab-Whipple, and we have 6 cases which received only inefficient treatment, but those were mainly patients who only received doxycycline for a short period of time. And most of the patients with the ceftriaxone and protein treatment. So actually we are performing a treatment trial which is randomized into 2 arms. We have the German standard ceftriaxone protein treatment versus the doxycycline hydroxychloroquine treatment, and the response is very good in both arms, so all patients are really well. But we have a problem with adverse events in the oral arm. That means we have a lot of patients, so 3 patients who have really strong problems with the photosensitivity from the doxycycline treatment, even if we advise them to don't go in the sun and to use the high protection and to wear hats and things like that. It is a problem with the German patients. And we have 2 cases who had allergic reactions against the treatment, so the treatment with doxycycline had to be stopped and switched to protein. So, just to summarize the findings concerning patients, I want to emphasize that iris is the most frequent complication during treatment, and that the patient with neurological involvement are at particular risk to run into problems during the treatment. So, and now we come up to the pathogenesis of Whipple's disease. Most of you know that because we did the most research on it, that the infection with tropholumab-Whipple is really frequent. And there's a discrepancy between the frequent occurrence of tropholumab-Whipple and the rareness of the Whipple's disease. So tropholumab-Whipple can be detected ubiquitously. There are a lot of subjects that are carriers of tropholumab-Whipple. Then we discover a protective humoral and cellular immune response in the most healthy person against tropholumab-Whipple. And tropholumab-Whipple is able to cause gastroenteritis, bacterial pneumonia, fever, and cough in some patients. And we find tropholumab-Whipple in around 6% of all patients with infectious endocarditis. And that was a thing that we just discovered some months ago. We were wondering if really how tropholumab-Whipple entered the body. And we did experiments where we incubated monolayers of epithelial cells with tropholumab-Whipple, and we incubated biopsies of healthy persons, related biopsies of healthy persons in an acid chamber with the bacteria. And there we see that the bacteria invade the epithelial layer, the green colored bacteria, really intracellular bacteria. And we see that also in the duodenal biopsies, the bacteria can enter with the lamina propria and can be found in cells in the lamina propria. And when we have a closer look at cells and at which cells the bacteria are ingested. We see that these are cells that are positive for HLA-DR, and for CD11C. That means they are antigen-presenting cells which are So the model for the infection is Verena Whipple, which is common, is that you have an acquisition with a pathogen and that it enters the intestine. That most people get some kind of family infection, sometimes probably in childhood. They develop an antigen-specific immune response, which leads to self-limitation of the infection, so that the people stay healthy and that they are able to defend against the pathogen. But in some patients there might be, or there is an immunological predisposition, the immunization by Verena Whipple itself is so strong that they develop the Whipple's disease, the chronic infection, where the bacteria get the opportunity to spread through the whole body and to proliferate massively in the microbiome. So one major question that is important for us is that since the immune reaction of the host decides about the cause of the infection, we wanted to define the immune deficiency that enables a chronic infection. That's one major point that I hope that I can clarify in the next minute. And another point is that in a chronic infection with Verena Whipple, the bacterium is spread all over the body, not only in the intestine, but we have a massive infiltration of the lymph nodes. We find it in the cerebrospinal fluid. In the brain, there is really a huge amount for the brain, a huge amount of pathogens which invades the cells in the skin. Here you see quite positive cells in all patients where we took samples from the skin. We really also find the patient. And of course, in the heart valves of the endocarditis patients, we find the bacteria, but also in the myocard or in the synovium, there's a huge infiltration with bacteria. And so the patients somehow tolerate the systemic spread of the agent, which is not typical for infections. So we suppose that there are immune regulatory mechanisms during Whipple's disease which enable the systemic spread and which avoid a massive immune reaction of the patient against the infection. So the normal way when which is active when intestinal infection occurs is that in the lamina propria, the image the little cells, the macrophages, which ingest the bacteria, the pathogens, the little cells get activated by molecules on the bacteria, and they will get mature and invade the lymph nodes, where they need CD4 T cells and get in contact with the CD4 T cell, present the antigens of the pathogen, which leads to the maturation of the T cells, so T effector cells can be generated. These effector cells re-invade the lamina propria, where they start to proliferate and start a CD4 triggered inflammation. And this inflammation then again enhances the activation of macrophages and enhances the maturation and recruitment of dendritic cells, so that the pathogens can be eliminated by the resident macrophages within the lamina propria. And after the successful initiation of immune responses, the pathogen should be eliminated, and then another mechanism has to start. The dendritic cell then switches their activation in the lymph nodes, and now the key effector cells are generated in regulatory T cells, and these regulatory T cells then also invade the tissues where the inflammation was present, and this leads to immune regulation, where the effector T cells are down-regulated, the reaction of the effector T cells, but also the activation of macrophages and dendritic cells is produced, so that you get a milieu of immunoregulation and loss of the effector T cells, which at the end results in homeostatic conditions where the lytic macrophages are quiescent and predominant inflammation in the tissue. And this mechanism is important to inhibit tissue and inflammation-induced damage of the tissue. So for the activation of CD4 T cells by nature-generated cells, you need some steps. And the first step is important for antigen presentation, and that the T cells have to recognize antigens which are presented by HLA-DR molecules. Then you need a second mechanism, the co-stimulation, which is provided by co-stimulatory molecules on the dendritic cells, which gets into contact with two molecules on the T cells. And this double contact leads to an activation of T cells to T effector T cells, which express CD40 ligand as a molecule. And then you have a third signal, a polarization signal, and from this polarization, the differentiation of this polarization decides about the polarization of the T cells. You might get when you have IL-4, you get Th2 helper cells, and you get TGF-beta in combination with IL-6, you get inflammatory Th17 helper cells, which produce IL-17 and IL-22, but for intracellular pathogens, the most important differentiation is the differentiation to Th1 helper cells, which produce huge amount of interferon gamma. And for this differentiation, the IL-12 that is provided by the dendritic cells is important. And then, after the initiation of the effector answer, for the initiation of regulatory T cell answer, there is important that you have enough IL-10 provided by the antigen-presenting cell, and the regulatory T cell expresses CD25, which catches away as a part of the IL-2 receptor, and it catches away the IL-2 that is necessary for the proliferation of effector T cells, and it expresses regulatory molecules like CTLA-4, which reduce activation after contact, and it produces regulatory cytokines like IL-10 and TGF-beta that are able to down-regulate immune responses. So, and some of these mechanisms we have analyzed in Whipple's disease patients. First, the dendritic cells. When you look at the lamina propria from calcium controlled with untreated Whipple's disease patients at the diagnosis or treated Whipple's disease patients, we have some dendritic cell markers. This is sign and marker for immature dendritic cells, and we see equal amounts of immature dendritic cells in the lamina propria. And this is also true for S100 positive dendritic cells, which represent nature dendritic cells. That's also no difference between healthy controls and disease patients concerning the amount of nature dendritic cells in the lamina propria. And we have a look at the distribution of Verena within the dendritic cells of the Verena mucosa. This is in fluorescence, where the nuclei are blue, gray is the skeleton of the cells, green is the Verena, red is the sign as marker for immature dendritic cells, and we see that Verena can be found in the immature dendritic cells of the lamina propria. When we look at the lymph nodes of untreated Whipple's disease patients and controls concerning the distribution of bacteria and dendritic cells, we see, like in the Verena mucosa, the distribution of disease-positive immature dendritic cells, and S100 nature dendritic cells does not different. It's not different between patients and controls. Of course, we see Whipple's disease bacteria only in patients. And they seem also to be within the immature dendritic cells. They are associated with the nature dendritic cells, but within the cells they are only found in the immature dendritic cells. So what we found is that immature and mature dendritic cells show equal distribution in the intestine and also in the lymph nodes of the disease patient, and Trophoboma vittri are located primarily in the immature dendritic cells. So when we go and look at the number of dendritic cells in the blood and the differentiation, most of the studies that we do is flow cytometry, so we analyze cells by expression of surface markers by flow cytometry. There we analyze dendritic cells according to their size, and there are several markers which exclude dendritic cells. They are negative for T cell markers, B cell markers, markers of natural killer cells and of monocytes. They express huge amount of HLA-DR, which is the DC population, and then we can distinguish several DC populations and the ones that are important for the defense against pathogens or pathogens, and the myriad dendritic cells of which additionally express CD11C. So exactly this population of myeloid dendritic cells is reduced in the blood of this way, graphs are controls. Here are the untreated patients and the treated with this disease patients. And we see that the untreated with this disease patients have a low amount of these myeloid dendritic cells in their polypharmacy. And when we look at the maturation of these cells, it seems normal. So we have CD86 as a co-stimulatory molecule that is normally distributed among healthy controls and the Whipple disease patients. CD86, also a co-stimulatory molecule, equally distributed. CCR7, which is a molecule that helps the dendritic cells to invade the lymph nodes, is also equally distributed. And CCR2, which is a receptor for the invasion of dendritic cells to inflamed tissue, is also normally distributed. So we have a reduced amount of myeloid dendritic cells within the peripheral blood, but it does not seem to be a problem of enhanced maturation, which would mean that the disease would invade the tissue and not stay in the peripheral blood. We have homeostatic conditions, and the disease of the Whipple disease patients are not in a higher mature state than the disease of the healthy controls. But if we then look at the activation of maturation of the dendritic cells after stimulation with antigenic components of bacteria, we see that again here include the healthy controls, untreated Whipple disease patients, and treated Whipple disease patients. We measure the CD86 as a molecule which indicates maturation of dendritic cells. You'll see that Trophoboma vittri induces slight maturation of the dendritic cells, and LPS, bacterial LPS, induces a high maturation rate of the dendritic cells, normally in healthy controls, but in Whipple disease this maturation is reduced. And more importantly, if you look at the production of iron-12, and we see that Trophoboma vittri is not able to induce any iron-12 production, also not in the healthy controls, while LPS induces iron-12 in healthy controls, but the iron-12 production of the patient is dramatically reduced. And this was now on DCs directly from the peripheral blood within the environment of the peripheral blood. There we see that the disease of Whipple disease patients do not respond appropriately to bacterial components, and that Trophoboma vittri itself delivers a weak stimulatory stimulus for the maturation of dendritic cells. So they stay in a semi-mature state, so to say, after incubation with Trophoboma vittri. When we now look at dendritic cells that are differentiated in vitro, that means they get all the cytokines that they need to mature in an in vitro system, and they are out of the milieu of the serum of the Whipple disease patient. Then we see that when we mature the cells without the serum components, then we get a normal maturation of the dendritic cells concerning the HLA-DR expression and concerning the CD86 expression, but the secretion of IL-12 still stays dramatically reduced in the Whipple's disease patient. So while healthy controls, the VC of healthy controls are able to produce huge amount of IL-12 already in the immature state, but more in the natural state. The Whipple's disease patients disease, they produce only very little amount of IL-12. So there seems to be no intrinsic effect of the dendritic cells to mature. This might be a problem of the milieu of the serum when they show a deficient maturation, but the reduced IL-12 production seems to be an intrinsic effect on the Whipple's disease patients' dendritic cells. So when we now look where the Trophoblema Whipple are located in the dendritic cells in vitro, we incubated immature dendritic cells with the bacteria for 30 minutes, and after that we stain for intracellular compartments and look where we find a co-localization of Trophoblema Whipple and markers of dendritic cells, but antigen-presenting components which are important for the identification of antigen. We see that the Trophoblema Whipple are also invested by immature dendritic cells, shown by the DC staining, but they are co-localizing with HLA-IDR molecules. So it seems to be that they're invested in a way that they really are entering components of the cell which are important for the presentation of antigen. So we suppose that they are really present. And to test if this presentation is really effective, we co-incubate CD4 cells with disease patients and controls with autologous dendritic cells to test their antigen stimulatory capacity. For that we mark proliferating T cells and look for their interferon gamma production. What we see is that what we see the disease patient in blue of controls when we use a general antigen like megalovirus antigens, we see that in principle these DC are able to present antigens and they are able to induce the antigen-specific reactivity of the T cell. But when we load the dendritic cells with Whipple antigens, we see that they are only able to induce the Whipple-specific T cell reactivity and the controls and the reactivity of the Whipple disease patient stays absent. So we see that the dendritic cells of Whipple disease patients, they are able to engulf the Trophoblema Whipple in vitro, and the Trophoblema Whipple associates with the components of the cells which are important for antigen presentation. And we see that the dendritic cells of Whipple disease patients are in principle able to generate antigen-specific Th1 responses, but they did not induce Th1-specific Th1 responses in the Whipple disease patients. So now we come to the T cells, and they are the ones which are important for the defense against these bacteria. We see again that there is controls untreated Whipple disease patients and treated Whipple disease patients. And what we see, it was described formally that Whipple disease patients have a reduced Th1 reactivity, which of course might be responsible for the chronicity of the infection. What we see is that when we look at the polyclonal Th1 response against STD, we see that only the untreated Whipple disease patients show a reduced reactivity, and upon treatment, the general Th1 reactivity returns to the normal level of healthy controls. And again, also when we look at the specific, in this case again, the megalovirus specific Th1 response, the untreated Whipple disease patients show a reduction of the immune response against the agent, but after treatment, the response turns to a normal response. This is not true for the Trophoblema Whipple specific Th1 response. All healthy controls show a pretty robust Th1 response against Trophoblema Whipple. but Whipple's disease patients are not able to elicit a liver-specific Th1 response, and the response does not restore upon treatment, so it stays absent also after effective treatment for the disease. And when we analyze the lymph nodes of patients, this is sustaining and indicates the proliferation of T cells, the general proliferation of cells within the tissue. It's a Ki67 staining, which is here shown in red, and the upper is in brown. We see that in the normal control lymph nodes, there is strong proliferation of cells within the germinal center, but also in the surrounding. In the Whipple's disease patient, we have this infiltration of the lymph nodes with the bacteria, but we see almost no proliferation within the germinal centers, and also outside the germinal center proliferation is reduced. The T cells of Whipple's disease patient in active disease show a very much reduced proliferation. So to summarize this data, we see a polyclonal and antigen-specific Th1 activity that is transiently reduced in the untreated Whipple's disease patient, but it restores after treatment. Only the Th1 response against Whipple's disease bacteria, it stays absent also after treatment, and we see a reduced proliferation of lymphocytes within the lymph nodes. When we now look at the cytokine milieu in the serum, it was described already that Whipple's disease patients have reduced amounts of interferon gamma, and we additionally looked at IL-17, which is also not enhanced in the patient. We see a dramatic increase in the IL-10 concentration in the serum of Whipple's disease patients before treatment and after treatment, and we see an enhanced expression of TGF-beta in the serum of Whipple's disease patients. And the same is true for the duodenal mucosa. When we look for secretion of cytokines, we see that the duodenal samples of Whipple's disease patients produce enhanced levels of IL-10, and they do not produce enhanced levels of inflammatory cytokines like IL-6, IL-6, IL-12, IL-1 beta, or TNF-alpha. So there is also in the blood and in the duodenal mucosa a regulatory milieu and the enhanced production of regulatory cytokines. Now that leads us to the idea that regulatory T cells may play an important role, and indeed when we look in the duodenal mucosa and we use FOXP3 as a marker for regulatory T cells, in the histology it's obvious that we have pretty much FOXP3 positive regulatory T cells in Whipple's disease before treatment. This number goes down upon treatment, whereas in healthy controls the regulatory T cells are found only very rarely in the duodenal mucosa. And this is here graphically demonstrated. We have low amounts of regulatory T cells in control and very high amounts of regulatory T cells in the Whipple's disease patients before initiation of treatment. And when we compare CD4 counts and regulatory T cell counts in the Whipple's patients, and we see that normally in healthy controls there are pretty much CD4 cells in the lamina propria, and in the Whipple's disease patient we see reduced amounts of CD4 cells. Normally during an infection, CD4 counts should be enhanced in the duodenal mucosa. And since the count of CD4 cells is reduced, the total percentage of regulatory cells among all CD4 cells is dramatically enhanced in the Whipple's disease patient. So in Whipple's disease patient before initiation of treatment, more than half of all the T cells in the lamina propria are regulatory T cells. When we do the same similar analysis in the peripheral blood, we don't see any changes in the amount of regulatory T cells in the peripheral blood, but what we see is that T cells of untreated Whipple's disease patients show enhanced expression of CTLA-4, which is an activation marker for regulatory T cells. So we were interested if the regulatory T cells show a higher regulatory potential than regulatory T cells for normal persons. For that, we divided for blood samples into total CD4 positive T cells and antigen-presenting T cells. These total CD4 cells were then divided in CD25 positive regulatory T cells and CD25 negative effector T cells, and the total T cell compartment was also included. The cells, the responder cells were marked with CFSE, which enables the monitoring of proliferation of the T cells, and then we integrated different combinations to look if the T cells, the regulatory T cells, are able to reduce unspecific T cell responses. We integrated effector T cells and regulatory T cells and compared it to the reactivity of only effector T cells. We have a look if the regulatory T cells included in this whole T cell population are specific in the downregulation of troponin-specific immune responses. We integrated only T effector T cells without the regulatory T cells, the antigen-presenting cells, and we integrated the total T cell compartment, which included the regulatory T cells with the antigen-presenting cells. So what we see is when we look at the general suppressive capacity, which means the downregulation of polyclonal immune responses, we see that in the normal healthy controls, the addition of regulatory T cells does not influence the polyclonal T cell response, but in the group of disease patients here in red, the regulatory T cells are able to downregulate polyclonal immune responses, which means that they are more effective than the regulatory T cells in healthy controls. And when we look at the Whipple-specific suppression of the regulatory T cells, there we see that there is no effect of the depletion of regulatory T cells from the Whipple disease patients' T cells. So we can conclude that the regulatory T cells of the Whipple disease patients are not the ones which are responsible for the reduced TH1 reactivity of the Whipple disease patients. So what we see concerning the regulatory T cells is that we have an enhanced percentage and number of regulatory T cells in the Verena, in the peripheral blood of the disease patients. Regulatory T cells show an enhanced activity, and we see that regulatory T cells are not the ones that are responsible for the suppression of the Whipple-specific TH1 reactivity. So at the final step in the immune reaction of the Verena should be macrophages. And what we found out earlier is that, and it was also discovered here, is that within the mucosa, we see here the infection with the Whipple bacteria, and the brown is marked a molecule which is CD163, that's a regulatory molecule in macrophages that express CD163, alternatively activated also called regulatory macrophages. And when we analyze these cells in Whipple disease patients compared to healthy controls here and compared to disease controls with other bacterial infections, we see that these regulatory macrophages or alternatively activated macrophages are dramatically enhanced in the untreated Whipple disease patients, but also in the treated Whipple disease patients. So there is an enhanced number of alternatively activated macrophages in Whipple disease patients. Peripheral blood, this looks similar. Also the monocytes of the peripheral blood show an enhanced expression of CD163 for the Whipple disease patients, and these, so to say, alternative activation of monocytes can be activated when we add troponin bacteria to the monocyte. So troponin is used to enhance this alternative activation. But this is true only for Whipple disease patients that in healthy controls, troponin is not able to enhance CD163. And when we now look at the bactericidal activity of the macrophages, we have the inducible nitric oxide synthetase, which is important to to synthesize nitrogen with relative nitrogen basics that are important for the defense against bacteria. We see that within the urea mucosa of the disease patients, the cyanose-positive macrophages are reduced compared to healthy controls and to disease controls. When we look at the production of nitric oxide in urea biopsies, we also see that control produced upon stimulation is a big amount of nitrogen, but it is reduced when we look at disease patients. And when we look at the IL-10 production directly in the monocytes, we see that upon stimulation with polyclonal stimuli and also with tropholimolipid, the monocytes of lupus disease patients are able to produce IL-10, also not normally stimulated on lupus, whereas the monocytes of healthy controls are not able to produce IL-10. So we can conclude that macrophages in the duodenum of lupus disease patients are able to be activated, and that would modulate the monocytes of the lupus disease patients. So, and since lupus disease patients show these special features for concerning their immune reactions, we were interested if during the immune reconstitution inflammatory syndrome, these regulatory mechanisms play any role, and if we can distinguish between patients which have a high risk for running into this immune reconstitution inflammatory syndrome can be identified by just monitoring red T-cell responses. We did some analysis on these patients. Just to give you a short introduction into the immune reconstitution inflammatory syndrome, the ILS manifests as an inflammatory flare-up of symptoms after initiation of treatment against lupus disease. Sometimes it is misinterpreted as a relapse of the disease, but when it's assured that the pathogen is eradicated, in most of the cases, this flare-up of inflammatory signs must be interpreted as immune reconstitution inflammatory syndrome. And it manifests at places within the body where probably the bacteria are also present. We have a lot of patients where it manifests in the joints or in the gut, but also in the orbital, the central nervous system, or the skin. This is the impressive picture where an inflammation of the orbita occurred in the lupus disease patient with iris. We have some patients who got blind after this iris syndrome of their eyes, and in patients with the involvement of the central nervous system, there are some cases where lesions within the central nervous system only occurred after the treatment, and which were interpreted firstly as a relapse or tissue when the proliferation of the pathogen occurs, but these regions were biopsied and we looked for where PCR and immunohistology for tropholimolipid, and there was no infection anymore. So these lesions within the cell had to be attributed to the iris reaction of patients. And the treatment, the only treatment at the moment that helps for the iris is immunosuppression. It can be done by cortisone or other drugs, but thalidomide is also a possibility for the German patient who still needs in most of the cases prednisone to treat the iris. And after high-dose cortisone, most of the patients get when we will look at the composition of the T-cells of the patients, we see here are the normal lupus disease patients, again untreated and treated. These are all paired samples. We see that we have an immunosuppression measured on the CD4 counts also during normal lupus disease. So we have reduced numbers of CD4 cells in normal lupus disease patients. But in the lupus disease patient which later develop iris, the CD4 counts are dramatically reduced there are patients which have only 50 or 100 CD4 count, which is really a strong immunosuppressed state of the patients. And not all of them, most of them have received immunosuppressive treatment for the diagnosis of lupus disease, but also a lot of these normal patients have received immunosuppressive treatment. So the initial count of CD4 cells really shows patients at risk to develop an iris after initiation of treatment, because the rising of the CD4 cells is much more prominent in the patients which later develop iris, where we look for the relation of the duration of the immunosuppressive treatment and the CD4 counts in the iris patient. We of course see that the longer the immunosuppressive treatment for initiation of therapy lasts, the lower the CD4 counts of the patients are. And when we now look at the activation of these CD4 cells, then we see that during normal lupus disease we have a high activation of CD4 T cells before start of treatment, so as a diagnosis of lupus disease, but after successful therapy, this activation of T cells goes down to normal levels, even below the levels of normal control. But this is not true for the patients which develop an iris. You see that they have relatively low levels of activation of the T cells before the start of treatment for lupus disease, but the activation rises dramatically after the initiation of treatment for lupus disease. And it rises to levels which are really higher than normal control. So this is the reconstitution of T cells, of the T cell department, is really a risk factor for the development of iris. And this, when we look how this activation is reflected by production of regulatory cytokines or inflammatory cytokines, this reflects the situation. We have a high amount of regulatory cytokines in the disease patient, which later develop iris before start of therapy, but this amount of regulatory cytokines dramatically falls down after initiation of treatment. And the opposite is true for the production of inflammatory cytokines. Patients which later develop iris have a low reactivity before starting of treatment, and this rises dramatically after the initiation of treatment. So this equilibrium, this immunoregulation and this activation seems to be the factor that drives iris. And these activated T cells, effector T cells, they invade then the tissues which are affected by iris. We see that here in the duodenum, for example, we have a huge amount of activated T cells in active iris. And also the example where the skin is monitored, where almost no naive T cells in the tissues, but a really high amount of activated effector T cells that invade from the capillaries, the tissue, and induce inflammation. And if we then analyze that perhaps there is the influence of the integrity of the duodenal mucosa, we have the idea that the duodenal mucosa and the integrity of the affected area would influence the appearance of iris. There we found earlier that, which we could not interpret correctly, that as I showed you before, the normal lupus disease patient has a high amount of regulation in the duodenal mucosa before start of treatment. But the iris patients, they have reduced or normal numbers of regulatory T cells in the duodenal mucosa. And this corresponds with the number of goblet cells within the duodenal mucosa, which when we assume that goblet cells protect the mucosal integrity, then we see that in the iris patients or the patients who later develop iris, the goblet cell index is very low, and the proliferation index, which also is a mechanism to protect the intestinal mucosa for damage. We have a high proliferation index in the normal lupus disease patient, but in the iris patients, the proliferation index is for starting therapy pretty low. So probably the intestinal mucosa is not protected in the patients who later develop iris, so that other pathogens or vitamin can induce much higher inflammation in the patients which later develop iris. So to summarize, that previous immune suppression enhances the risk to get an iris, and the quality of the T-cell reconstitution influences the pathogenesis of iris. So here's just a short summary of immunopathology. We see that the maturation of dendritic cells is inherent in the Whipple's disease patient, and the most important thing is that there will be a deficient alpha production, which prevents proper induction of proper Th1 reactivity. The chronic infection, this pathogen reduces proliferation of lymphocytes, and the transiently reduced Th1 reactivity. We think that regulatory T cells are the phenomenon population in the genome of untreated disease space, and that they protect the tissue for the damage that would be induced by the infection with pathogen. We see that enhanced immune suppression is a major risk factor for the development of iris, and that the quality of the T-cell reconstitution influences the pathogenesis of iris. Just to give you our current model of the pathogenesis of Whipple's disease patients, here's a short pathogen. So we believe that I hope that I could show you that at the beginning of the infection, dendritic cells and macrophages are often engulfed totally by nucleus, and CD4 cells are present. We see that the dendritic cells show a reduced activation and reduced maturation. Also, they are able to invade the lymph nodes, but there are semi-mature dendritic cells that invade the lymph nodes. In the following, there is no proper Th1 response induced, but more a T-regulatory response, which leads to an energy of the effector T cells and the proliferation of the regulatory T cells, which are enhanced activated. And following the regulatory T cells invade the urinary mucosa and lead to immune regulation of dendritic cells and macrophages, which in the end induces this typical picture of Whipple's disease where macrophages are inactivated and which leads to the persistence of the pathogen. And last but not least, the dendritic cells which are able to migrate to the body might be responsible for the systemic spread of the bacteria. So I just thank you for your attendance, and I hope that I can shed some light on the pathogenesis of Whipple's disease, and all these co-workers who helped us a lot with our studies, and I hope will help us in the future also to get new insights to the pathogenesis of Whipple's disease. So thank you. To some of them. Only we do not do this often, but when we are relapsing disease and we are not able to cure them with several antibiotic regimens, then we choose the Whipple gamma. But I think 4 patients.
I've never experienced that. If we have somebody escaping treatment, we've never had, well, it's happened. We get, I don't know, maybe 28 patients that's failed by receiving cosmetic development, but it's never happens to those
these patients who receive interferon gamma or receive actually interferon gamma, they have also doxycycline. They have first, normally they have the salt and protein combination, and when that fails, then they get a doxycycline and chloroquine up, and that also fails.
What was your preparation for failure?
Resistance of histological and PCR resistance of the pathogen in different tissues. don't see a histological remission in the glomerular mucosa. Most of the patients have to have a neurological involvement. So they really have upcoming new neurological symptoms after the antibiotic treatment, and this, the brain biopsy or the cerebrospinal fluid PCR positive, and the bacteria could be cultivated. Active bacteria.
Well, I think that the thing with the PCR is bizarre. I think we will have a final explanation. We need a little bit more work to explain why PCR's negatives were, despite the fact that people are very, very still infected. So usually after 1 month you don't have a PCR positive, but people are still infected and very infected.
Yeah.
So this is very. I think we'll find out.
No, it's not for 1 month. They were treated for 1 year, of course.
Yeah.
They were not treated only for 1 month.
It's happened something. I remember one case, I don't know if there is another one. There is one case, he was cured, but he got PCR all his life positive. Very bizarre. We get one case. It was well, but it's never been negative.
In the duodenum, I'm not scared about the positive PCR in the duodenum. That's not something that...
No, it was true. It was positive.
Yeah, that's what I think what can happen, but when the cerebrospinal fluid stays positive or gets positive after initial negative, being initial negative, then I'm worried about. We had this one patient which were only involved for 10 or 15 years, he was positive in the cerebrospinal fluid, but they never were able to cultivate the bacteria. It was PCR positive. I think by now he was able to see the bacteria in the microscope, but they were not. It wasn't a patient who no, they never saw the patient.
There's a patient with the arm that was treated.
He was in the 80s. He was treated with interferon gamma, but the cerebrospinal fluid never got negative. And if he was good for 10, 20 years, I think 89 was his diagnosis. And he ran into problems 2 years ago. The PCR was still positive, it was positive.
I think it's not this case where you get this PCR positive for long without clinical sign, and he sent us the CSF and we isolate the strains. We get the strain.
You have the strain, I thought it never was out.
Oh yeah,
okay. But
we get the strain.
And he ran into problem only 20 years after the first diagnosis.
It's a slow disease.
And he had antibiotics for 10 years of his life, and finally it's interferon.
Yeah, it's a relapse and relapse and relapse.
So very few patients have these problems with these problems.
I think they may relapse later today.
Yeah, probably.
I think the main problem is that there is, until recently, there was not very few centers where people get a very long follow-up to see patients relapsing after 3, 4, 5 years. And specifically to relapse, in the neurological relapse, many people will miss this concept, just say, well, it's dementia or whatever, and they will die without diagnosis of glucose. I think it's probably that one.
Yeah, that's true. The patients that we monitor are from the mid-90s. So this is a very early case, but that is monitored for a longer period of time. Most of them are diagnosed mid-90s, so they are monitored now for almost 20 years.
Current hypothesis is that the people who get Whipple disease are lifetime susceptible
to that's what I think.
And we treat them for lifetime.
Yeah, well, that's what we also believe, and the immunological data, they will prove that we have no TH1 reactivity. It does not come back even after 20 years, and they have no TH1 reactivity, and they are susceptible. That's what I believe.
You have seen this lady that relapsed 5 times, and then we found out that the strain was different. We were cured, so it's not our fault. Cure the lady.
Yeah, of course.
That's our fault.
She got infected by another strain.
Specifically because when they infected this time, all the family is infected.
Yeah,
it's very contagious. So 50% of the family is infected. So even if you sterilize the lady, she will be infected by the family. But probably it's towards the end.
Yeah, that's what we also, of course, I agree completely that the susceptibility lifetime, the theory in Germany is favorized in that the second infection will be too late. Patients are too old, and the second infection, in most of the cases, or in almost every case, will be at the time point where the patient is not alive anymore.
Well, they live longer.
Yeah, I know. Now our patients also live long. They also go into the 80s or the 90s, and they really get also these patients that I'm aware are also old. It's not that they die at 71 by some undefined reasons. They are old. They don't die very early. And the theory is that if it lasts 40 years to develop the whole picture of the disease and to get the symptoms that are really life-threatening, then they are too old. Then probably a patient which was 60 at the first diagnosis, or even 75, who will not live anymore when he relapses. Yeah, no, it's really a different. I'm not a physician, so probably when I would have myself would be affected from this disease, I would also take antibiotics to the end of my life. Yeah.
Yes.
J'ai d'autres questions? Merci beaucoup.